Local scientists have made an exciting discovery on the seafloor along the Cascadia Subduction Zone.
On January 8, 2025, seismic monitors worldwide picked up a series of unusual tremors. A 3.4 magnitude quake shook parts of Greece, while subtle but persistent rumblings began surfacing along two of the United States' most dangerous fault zones, the San Andreas Fault and the Cascadia Subduction Zone. These events aren't random. They point to mounting stress in Earth's crust and reignite concerns about the Big One, a potentially catastrophic earthquake that could devastate the West Coast. Are these tremors early warnings or merely a reminder of the restless forces beneath our feet? Rising seismic activity in California. The San Andreas Fault stretches over 800 miles, dividing the Pacific and North American tectonic plates. This iconic fault line has been the site of countless earthquakes, including devastating events like the 1906 San Francisco quake, with a magnitude of 7.9, which took over 3,000 lives and leveled the city. Divided into three segments, northern, central, and southern. The southern segment is of particular concern due to its prolonged silence. Recent USGS data indicates several minor earthquakes along the fault line in 2024 and early 2025. For instance, in December 2024, a 4.7 magnitude quake struck near Parkfield, often dubbed the earthquake capital of the world, because it sits on a highly active section of the San Andreas. On January 5, 2025, another series of tremors, each between magnitude 2.1 and 3.5, occurred near San Bernardino, closer to the vulnerable southern segment. While these quakes aren't alarming on their own, their proximity to major population centers amplifies concern. Historically, the southern section hasn't experienced a massive rupture since 1857, when the Fort Tejon earthquake, with a magnitude of 7.9, ruptured 225 miles of the fault. Since geologists believe large quakes occur here roughly every 150 years, the Big One may already be overdue. The tension from the grinding Pacific and North American plates increases yearly by approximately 30 to 35 millimeters, slowly inching toward a breaking point. Clusters of seismic activity have surfaced along the San Andreas Fault over the past few months, including areas like Hollister and Coachella. According to Dr. Lucy Jones, a renowned seismologist, clusters of small tremors may signify increased movement deep within the fault. However, while these earthquake swarms are not unusual, their location and frequency often point to heightened activity along stressed segments. A closer look at the southern San Andreas in recent months shows irregular patterns. Between November and January, more than 20 tremors exceeding magnitude 3.0 were detected, a sharp uptick compared to previous years. In addition, long-period ground displacements, where the ground shifts without causing sudden tremors, have been detected using advanced GPS sensors. This silent motion, called creep, may indicate accelerating stress along the fault. Experts warn that swarms might precede larger events. In 2016, a similar swarm near the Salton Sea raised alarms because it occurred near a fault that connects to the San Andreas. While no major quake followed, studies revealed how close the system came to triggering a larger event. Dr. Jones warns that foreshocks are only sometimes identifiable until after a significant quake occurs. We don't know when or where the energy will be released, but the increasing activity is something we need to monitor closely, she says. Not just in one specific spot or in a specific window of time, but all over the region. Cascadia Subduction Zone, the long-term risk. The Cascadia Subduction Zone is a 620-mile fault stretching from Northern California to Vancouver Island, Canada. It marks the boundary where the small Juan de Fuca plate slides beneath the much larger North American plate. This collision creates immense geological stress, which, when released, can produce megathrust earthquakes of catastrophic magnitude. The significance of the CSE in seismic research is immense. Unlike transform faults like the San Andreas, subduction zones are capable of generating earthquakes exceeding magnitude 9. The plate's movement also drives volcanic activity in the Pacific Northwest, contributing to the formation of the Cascade Range. The sheer potential for destruction in Cascadia has made it one of the most closely studied faults worldwide, with scientists racing to understand its behavior. Historically, the CSC is infamous for generating massive seismic events. The last megathrust earthquake struck in January 1700, estimated at a magnitude of 9, causing violent shaking and a massive tsunami that reached the coasts of Japan. This event, uncovered through oral histories of indigenous peoples, geological evidence of ghost forests, and Japanese tsunami records, underscores the region's volatile past. In recent years, seismic sensors have recorded significant tremors along and near the Cascadia Subduction Zone, highlighting its ongoing activity. In November 2024, a magnitude 5.2 earthquake struck roughly 120 miles off the Oregon coast, followed by a magnitude 4.8 tremor in December near the same region. Most recently, in January 2025, a swarm of minor earthquakes ranging from magnitude 2.5 to 3.9 was detected offshore of Washington state. These earthquakes, while not immediately dangerous, have captured scientists' attention due to their locations and depths, often occurring along the locked zone. This part of the fault remains stuck due to immense friction, periodically building energy until it releases in a major quake. Many tremors also fall within the region where episodic tremor and slip occurs, a phenomenon where plates move silently for weeks, signaling stress transfer deeper into the fault. Additionally, GPS observations show that parts of the Juan de Fuca plate are shifting slightly faster, possibly indicating increased interaction with the North American plate. This subtle motion could precede a larger event, though its timeline remains uncertain. The last major Cascadia earthquake in 1700 remains a haunting reminder of the fault's potential. Researchers estimate such megathrust quakes occur every 300 to 500 years, placing the region near the average interval for another event. The destruction from a magnitude 9.0 quake could rival or exceed that of recent disasters, like the 2011 Tohoku earthquake in Japan. A major Cascadia event could cause prolonged shaking, tsunamis, and widespread coastal destruction, threatening cities like Seattle, Portland, and Vancouver. Scientists remain divided over when the next big one might strike. Some suggest that the observed seismic activity could reflect typical patterns for a subduction zone, while others, including researchers from the Pacific Northwest Seismic Network, argue that the frequency of deep tremors may be an early warning. But this is just one of the things we need to focus on here. Observing other global seismic events. Texas has seen an increase in earthquake activity over the last decade, primarily tied to human activities such as oil extraction. The link between these events and hydraulic fracturing or wastewater injection has been studied extensively, showing how these practices create imbalances in underground pressures. This destabilization triggers what are known as induced earthquakes. Historically stable areas, like the Permian Basin and Dallas-Fort Worth, are now experiencing frequent seismic events. A notable example occurred near Mentone in 2022, when a magnitude 5.4 earthquake struck, followed by a series of smaller tremors across West Texas. Researchers identified that deep wastewater injection disrupted pre-existing fault lines, increasing seismic stress. While some experts argue these quakes are limited to shallow, localized systems, others caution about the long-term effects, especially the potential destabilization of larger, deeper faults. Monitoring and mitigation efforts by organizations like the USGS and Texas Railroad Commission are ongoing, but debates persist about whether stricter regulations are necessary to reduce future risks. Beyond Texas, seismic activity in other parts of the United States underscores the region's complex geological dynamics. In Northern California, smaller earthquakes near Lake Almanor and the eastern Sierra Nevada provide valuable insights into fault stress changes. Southern California's Imperial Fault Zone, located near the US-Mexico border, has also recorded swarms of tremors that have drawn attention due to their proximity to the San Andreas Fault. These seismic clusters raise concerns about how stress transfer could potentially elevate the risk of larger events. Together, these occurrences highlight the importance of comprehensive monitoring networks and continued research into how smaller quakes might connect to broader fault systems. Globally, seismic activity along the Ring of Fire has intensified, with significant earthquakes reported in Vanuatu, Indonesia, and the Philippines. These regions, situated along major tectonic plate boundaries, are particularly prone to large-scale seismic events. Recent earthquakes in Vanuatu and Indonesia have registered magnitudes between 6.0 and 7, leading to localized damage from shallow quakes capable of generating tsunamis or landslides. Meanwhile, Nepal has experienced moderate seismic events resulting from the Indian plate's ongoing collision with the Eurasian plate, adding strain to the region's already stressed tectonics. The Philippines, which combines subduction zone dynamics with active volcanic systems, frequently endures moderate to large tremors that exacerbate geological risks. Though seismic events are generally confined to specific regions, some researchers suggest a broader interconnectedness through stress redistribution across tectonic boundaries. This phenomenon, known as dynamic triggering, describes how significant earthquakes in one area can influence activity thousands of miles away by altering stress along other plate margins. While these connections remain subtle and often challenging to track, they emphasize the importance of understanding global patterns to predict seismic risks more accurately. As seismic monitoring technology improves, efforts to correlate regional and global activity continue to provide critical data for forecasting future hazards, opening up the doors for us to study them inside out. Understanding the Mendocino Triple Junction. The Mendocino Triple Junction, located off the Northern California coast, is a vital geological intersection where the Pacific Plate, the North American Plate, and the Juan de Fuca Plate meet. This complex boundary region is one of the most seismically active zones in North America, due to the dynamic interactions between these tectonic plates. The Triple Junction transitions the motion of the Pacific Plate sliding northwestward against the North American Plate along the San Andreas Fault to the subduction of the Juan de Fuca Plate beneath the North American Plate at the Cascadia Subduction Zone. These processes generate significant tectonic stress, shaping seismic activity in the region and influencing larger-scale geodynamics across the western United States. In December 2024, a magnitude 6.9 earthquake struck near the Mendocino Triple Junction, emphasizing its seismic importance. Occurring along the Mendocino Fault Zone, the quake was relatively shallow and caused tremors felt across northern California and southern Oregon. Scientists observed a connection between this event and prior clusters of moderate earthquakes along nearby fault segments. The event's aftershocks highlighted the ongoing tectonic stress accumulation in the region, particularly where the San Andreas Fault system meets the Triple Junction. Analysis suggests that stress from the 2024 quake may have transferred to adjacent fault systems, potentially elevating the risk for larger events. The Mendocino Triple Junction poses a unique threat scenario due to its capacity for complex ruptures. Seismic models consider the possibility of simultaneous or cascading ruptures involving the Mendocino Fault, Cascadia Subduction Zone, and even segments of the northern San Andreas Fault. Such an event could generate a multi-fault rupture, significantly magnifying its impact. While geologists emphasize that these scenarios remain speculative, the Triple Junction's history of high seismicity demands continued monitoring and research. Predictive studies estimate a high likelihood of moderate to major quakes occurring every few decades in this area, which could have regional and global tectonic implications. The Mendocino Triple Junction remains a crucial focus for seismic research, not only for understanding earthquake potential in California, but also for grasping the broader mechanisms governing plate tectonic interactions. The region's combination of slip, subduction, and compression processes underscores its importance in assessing seismic hazards for the Pacific Northwest. Further investigations into this dynamic intersection may offer invaluable insights into predicting future earthquakes and improving resilience across vulnerable communities, maybe in time for a mega earthquake to be avoided. The Cascadia Megathrust Earthquake Risk. The Cascadia Subduction Zone poses one of the most significant earthquake threats in North America. A megathrust earthquake in this region could reach magnitudes exceeding 9, releasing energy far greater than typical fault-based quakes like those along the San Andreas Fault. The primary danger lies in the immense size of the rupture zone, spanning 700 miles from northern California to southern Canada, allowing the fault to unleash seismic waves capable of devastating urban and rural areas alike. The intensity, combined with prolonged shaking, could cause widespread structural collapse, landslides, and liquefaction, compounding the catastrophe. Equally alarming is the potential for a tsunami triggered by a Cascadia megathrust event. A sudden slip along the fault would displace massive volumes of ocean water, sending waves racing toward the coasts at speeds exceeding 500 miles per hour. Coastal communities in Oregon, Washington, and parts of California are particularly vulnerable due to low-lying areas that offer little natural protection. Historical models, like the 1700 Cascadia earthquake, indicate tsunamis could reach heights of over 100 feet in some areas, sweeping away infrastructure and endangering millions. Efforts to compare Cascadia's risks with the San Andreas Fault often emphasize that while both are dangerous, Cascadia's tsunami potential and sheer scale of destruction place it in a league of its own. Risk analysis highlights the urgency of preparing for a Cascadia megathrust event. Geologists studying seismic gaps estimate that Cascadia has exceeded its average recurrence interval for major earthquakes, suggesting the region is overdue for another catastrophic rupture. Strain accumulation data reveal significant stress along the fault, pointing to a growing likelihood of a large-scale release. Despite this, uncertainty persists about precisely when such an event might occur. Many scientists view preparation, rather than prediction, as the key to mitigating impacts. Coastal communities have begun building tsunami evacuation infrastructure and enhancing building codes to endure prolonged shaking. While scientists continue to map and study the Cascadia Subduction Zone, its risks underscore the need for vigilance and investment in disaster resilience. The ability to withstand the effects of a megathrust earthquake and its associated tsunami depends on proactive planning, informed by data and historical precedent. For those living along the Pacific Northwest coast, the clock is ticking toward an event with the potential to redefine life in the region. The stress transfer mechanism. The science of stress transfer provides critical insight into how earthquakes influence the behavior of adjacent faults, creating ripple effects that may trigger additional seismic events. Stress transfer theory posits that when a fault ruptures during an earthquake, the surrounding crust either absorbs or redistributes stress, sometimes increasing strain along nearby faults. This redistribution can make previously dormant faults more likely to rupture, escalating the risk of subsequent earthquakes in the region. For California, this mechanism has critical implications, especially for the San Andreas Fault, which intersects several smaller but still active fault systems. Clusters of seismic activity, ranging from swarms of small quakes to patterns of aftershocks, demonstrate how stress redistribution unfolds over time. Aftershocks are particularly significant, as they often occur along portions of a fault that did not slip during the main event, allowing accumulated strain to adjust. While most aftershocks are smaller than the initial quake, some can be unexpectedly large, as they act as precursors to new fault ruptures. In California, understanding these clusters aids researchers in identifying areas most at risk for future seismic activity. Geological models simulate these interactions, mapping how the energy released from one event transfers through the Earth's crust and potentially reactivates surrounding faults. Historical data from major San Andreas Fault earthquakes highlight how stress transfer has played a role in seismic sequences. The 1906 San Francisco earthquake, estimated at a magnitude 7.9, generated aftershocks along its length and likely influenced stress levels on nearby faults. Similarly, the 1989 Loma Prieta earthquake resulted in a cascade of aftershocks and increased strain in nearby regions, raising long-term concerns about stress accumulation along less affected sections of the fault. While no immediate rupture followed, subsequent geological studies revealed that strain energy remained high, particularly in the southern stretches of the San Andreas Fault. Geologists continue to refine models predicting fault behavior after significant earthquakes. Advances in seismology, such as GPS measurements of crustal motion and computer simulations of stress interactions, have enhanced predictions of fault movement. These models suggest that even small earthquakes can lead to cascading effects, underscoring the interconnectedness of California's fault network. While precise prediction remains elusive, identifying stress transfer patterns offers a vital tool for hazard assessment and preparedness efforts. But there's a lot more to it. Seismic gaps and forecasting future earthquakes. Seismic gaps, areas along a fault where significant earthquakes have been notably absent, hold critical importance in understanding earthquake forecasting and risk assessment. These gaps indicate portions of a fault system where tectonic stress has continued to accumulate without being released, suggesting a heightened risk for future seismic activity. Unlike fault segments that rupture more frequently, seismic gaps act as silent warnings of the strain buildup beneath the Earth's surface, often preceding highly destructive events. Scientists have identified seismic gaps as essential tools for forecasting potential earthquake hotspots. By studying fault segments with long intervals of inactivity, they can estimate where the most significant stress remains and project the probability of a rupture. In Northern California, the Messino Fault has emerged as a point of concern due to its prolonged dormancy. Although seismic activity has been observed in nearby regions, this particular fault line has not experienced a significant rupture in decades. This quiet period raises concerns that the stress buildup along this segment may contribute to a future earthquake with potentially catastrophic consequences. Historically, seismic gaps have often preceded major seismic events. A well-documented example includes the devastating 1964 Alaskan earthquake, which occurred in a region with a pronounced seismic gap along the Aleutian Subduction Zone. Similar patterns were observed prior to the 2004 Indian Ocean earthquake, which followed decades of inactivity in the subduction zone off Sumatra. These examples underline the predictive value of seismic gaps in highlighting high-risk regions, prompting heightened monitoring and preparedness efforts. Northern California provides a compelling study area for understanding seismic gap behavior, particularly around interconnected fault systems such as the San Andreas and Cascadia Subduction Zone. Combining historical patterns with real-time monitoring, scientists are working to refine earthquake forecasting methods. Techniques such as GPS measurements of surface deformation, satellite imagery, and seismic tomography enable researchers to pinpoint areas of high stress and better anticipate potential ruptures. While forecasting remains an inherently complex science, seismic gaps serve as a focal point in the pursuit of mitigating earthquake risks in vulnerable regions. Advances in seismic detection and monitoring. Modern advancements in seismic detection and monitoring are transforming the way we understand and respond to earthquakes. Central to these developments are highly sensitive devices such as seismometers, GPS instruments, and strain sensors. Seismometers, placed strategically along fault lines, detect ground vibrations and measure their magnitude and frequency. Meanwhile, GPS systems monitor the subtle shifts in tectonic plates, offering insights into stress accumulation. Strain sensors, capable of identifying minute deformations in the Earth's crust, add another layer to detecting potential earthquake precursors. Together, these tools enable researchers to compile detailed models of seismic activity. Agencies like the USGS and international bodies rely heavily on these technologies to track global earthquake patterns and provide critical data in real time. Despite these advances, seismic monitoring faces significant challenges. Predicting the precise timing, location, and magnitude of earthquakes remains elusive due to the complexity of tectonic processes. For instance, while it is possible to identify zones under stress, the mechanisms that trigger a fault rupture can be influenced by a range of unpredictable factors. Additionally, delays in earthquake reporting highlight the limitations of detection networks, particularly in remote or under-monitored areas. For the public, early warnings may sometimes arrive only seconds before shaking begins, limiting preparedness. These gaps emphasize the need for broader network coverage and real-time analysis. Efforts to overcome these limitations have led to promising innovations. Enhanced early warning systems, such as the Shake Alert program on the US West Coast, aim to notify residents seconds to minutes before an earthquake strikes, allowing time to take life-saving actions. Researchers are also exploring artificial intelligence and machine learning to analyze seismic data more effectively and predict potential patterns. Beyond detection, investments in earthquake-resistant infrastructure and community preparedness programs are vital for reducing the impact of future seismic events. Together, these advancements not only improve our ability to monitor earthquakes, but also enhance society's resilience against their devastating effects. We need to, because if we're not prepared, things could get bad, fast. Potential economic and societal impact of earthquakes. Earthquakes present considerable risks to infrastructure, particularly in regions that are at high risk for seismic activity. In densely populated areas like the San Francisco Bay Area and Seattle, the potential damage from a major earthquake is staggering. The San Francisco Bay Area, for example, is particularly vulnerable due to the San Andreas Fault, which poses a constant threat. Key infrastructure, such as bridges, highways, and public transportation systems, could be severely compromised during a significant event. The collapse of structures similar to the Loma Prieta earthquake in 1989 demonstrates the extensive damage that can occur. In 1989, The collapse of the Oakland-San Francisco Bay Bridge and the damage to the San Francisco-Oakland area caused billions in damages and led to more than 60 fatalities. In Japan, the 2011 Great Tohoku earthquake caused widespread destruction to buildings, infrastructure, and utilities, leading to significant disruptions and nearly 20,000 deaths. These case studies serve as reminders of how vulnerable infrastructure in earthquake-prone areas is and how much work remains to mitigate these risks. The economic costs of earthquakes extend far beyond the damage to infrastructure. Business operations in affected regions may come to a complete halt, leading to lost revenue, layoffs, and long-term economic instability. The 1994 Northridge earthquake in Southern California, for example, led to insurance payouts surpassing $44 billion and forced several businesses to close their doors for weeks, and in some cases, permanently. The global supply chain can also be disrupted when critical ports, highways, and manufacturing facilities experience substantial damage. Furthermore, beyond the immediate loss of life and property, economic recovery can take decades, placing a significant burden on local, state, and federal governments that must allocate resources for rebuilding and support services. Governments, insurance companies, and private entities are increasingly focusing on proactive efforts to minimize these risks. These include retrofitting buildings to higher seismic safety standards, investing in earthquake-resistant infrastructure, and developing advanced early warning systems. On the societal front, earthquakes can profoundly impact daily life. The immediate loss of essential services, such as electricity, water, and communications, can leave communities isolated and in turmoil. Government response strategies generally involve emergency management protocols that activate once an earthquake occurs. These protocols include evacuations, rescue missions, and the establishment of temporary shelters and medical facilities. Awareness campaigns in earthquake-prone areas aim to educate citizens on how to respond to seismic events, including evacuation drills and instructions on securing homes and offices. Public response is crucial to minimizing casualties and preventing further harm. Despite these efforts, the emotional toll on survivors can be substantial. People may experience a range of psychological reactions, such as post-traumatic stress disorder, anxiety, and depression. In the longer term, efforts to rebuild affected communities may span years and require long-term commitment from governments, businesses, and local residents to return to a state of normalcy. Ultimately, earthquakes present a complex blend of risks: economic, social, and infrastructural. Understanding their impact is essential in developing better prepared communities capable of withstanding the immense challenges they present. The cost of inaction and complacency is evident in past earthquakes, and future events will necessitate stronger, more coordinated responses, although it's not as simple as it might seem. What are the experts saying? As seismic activity in both California and the Pacific Northwest continues to escalate, geologists and seismologists are voicing concerns regarding the potential for a larger-scale earthquake. These experts are closely monitoring a variety of signals, from frequent tremors along the San Andreas Fault to increasing seismic activity in regions such as the Cascadia Subduction Zone. According to leading seismologists, the risk of a significant seismic event in these regions remains high. They point out that California's San Andreas Fault is a major source of concern due to its history of large earthquakes, most notably the 1906 earthquake that devastated San Francisco. Given the ongoing tremor patterns, many experts believe that an earthquake of comparable magnitude may be due, with models predicting that seismic stress could soon reach a breaking point. In the Pacific Northwest, the Cascadia Subduction Zone poses a significant threat as well. Experts have long warned about the potential for a megathrust earthquake, an event that could exceed magnitude 9 and trigger massive tsunamis along the coastline. Long-term predictions, however, remain a mix of caution and uncertainty. Experts largely agree that the probability of a significant earthquake in both California and the Pacific Northwest is high within the next few decades. The frequency and intensity of tremors suggest the gradual buildup of tectonic stress, which could eventually lead to a larger, more catastrophic event. However, precisely predicting when such an event will occur is another matter entirely. Currently, there are no definitive ways to forecast earthquakes with precision. The science of earthquake forecasting is still evolving, and many variables contribute to the uncertainty of exact predictions. Instead of pinpointing exact dates or times, many experts focus on the likelihood of earthquake occurrence within a given period, highlighting seismic activity as an ongoing and persistent risk that requires constant vigilance. While long-term predictions may not offer certainty, mitigation strategies are a subject of significant focus in the seismological community. As the science behind earthquake prediction continues to develop, mitigation efforts focus more on resilience, making communities more prepared to handle major earthquakes when they occur. Experts widely advocate for improving building codes, ensuring that structures in earthquake-prone regions can withstand the significant forces of a large quake. Retrofitting older buildings, which were built without modern seismic safety measures, has become a major priority in cities like San Francisco and Los Angeles. Additionally, earthquake-resistant infrastructure, such as reinforced bridges and tunnels, is being increasingly implemented to reduce the devastating impacts that an earthquake could have on transportation and communication networks. Early warning systems are another key element of seismic risk mitigation. Recent advances in seismic detection technology have enabled more timely alerts, providing valuable seconds or minutes for individuals to take cover or for infrastructure to be shut down before damage occurs. Several states, including California, are testing and refining systems to warn people about shaking in advance. While these alerts are still in their infancy and cannot fully predict the size of an event or exact impact, they represent a major step toward improving public safety and reducing fatalities. Overall, experts agree that while the exact timing of major seismic events remains elusive, there are clear and pressing steps that can be taken to lessen the human and economic costs of large earthquakes. Increased investment in research, resilient infrastructure, and public preparedness will play a significant role in minimizing potential damages when the inevitable occurs. But can we really get ahead of it? What do you think? Leave your thoughts in the comments below, and if you like this video, don't forget to subscribe to our channel. See you in the next one.